welcome all of you. In the last couple of classes, we started discussing about multiple quantum NMR. We extensively discussed and we understood for multiple quantum the transitions that are other than plus or minus 1, where change in the magnetic quantum number delta AM between any two energy states is other than plus or minus 1 are called multiple quantum. They are forbidden transitions, you cannot directly detect them, that is what I said. But however, indirectly we can detect them. That we saw that in one of the pulse sequences in the homonuclear multiple quantum NMR, how we can detect multiple quantum NMR spectrum. What is the basic requirement for multiple quantum to be detected? I said the spin systems should be coupled. You can have 2 or 3 spins or 4 spins, n number of spins coupled. One of the coupling may be 0, no problem, but they should be part of the coupled spin system. And the coupling should be reflected in the NMR spectrum. Only then we can see multiple quantum. That is what we observed. And also we took the example of 0 quantum and double quantum of 2 coupled spins. Then we observed for the double quantum transition, the 2 spins will be simultaneously flipping in the 2 spin case, and there is no passive spin to give rise to coupling. As a consequence, the local field is only the sum of the chemical shifts. So, in the double quantum NMR of 2 coupled spins, you get a single peak at the sum of the chemical shifts of 2 coupled spins, and there is no splitting, a single peak. On the other, for the 0 quantum of 2 coupled spins, we get a peak at the difference of the chemical shifts, and yet again there is no passive spin. As a consequence, there is no splitting of that transition. So, you get single peak for double quantum and 0 quantum of 2 coupled spins. And the chemical shifts also we know at some and difference of chemical shifts for DQ and ZQ. We also went to the multiple quantum of 3 coupled spins and more also. Just to understand the splitting pattern, we went to the we understood the coupling pattern DQ and ZQ of 2 spins in 3 coupled spin systems. Now the third spin is a passive spin. If I take 3 spins, there are 3 possibilities of double quantum. Consider A, M and X. There could be AM double quantum, AS double quantum and MX double quantum. All the 3 are there. And the passive spin is the third spin. So, that gives rise to splitting of the double quantum line, double quantum transition, because of the 2 spin states of the passive spin. So, double quantum and 0 quantum spectrum of 3 coupled spins are going to be doublets. And we understood what is the frequency, what is the sum, where it comes, and the separation, what is the separation, etc. The separation of the double quantum in a 3 spin case is it is the sum of the J coupling between active spins and passive spins. We extend similarly for ZQ, it is difference of the coupling between active spin and passive spins. That also we understood. And when we went to 4x, 4 spin, 5 spin, 6 spin example, we understood how many transitions one can get in different spin system, coupled spin system, how many multiple quantum spectra transitions are there in different quantum. And in the 4 spin case, we also saw what happens if you go to DQ, then 2 are passive spins, and each passive spin will couple to 2 spins, gives us a doublet with some separation, and another active spin couples to the 2 passive spins, gives us to another doublet. Like that, we get 2 sets of doublet, 4 lines will be there, and one larger separation correspond to one sum of the couplings, and smaller separation correspond to one sum of the couplings. Like this, we extended and understood everything, and then we understood a pulse sequence for the homonuclear multiple quantum detection, and also we understood how we can utilize this to understand the relative signs of the coupling in a weakly scalar coupled 3 spin case A, M and X. We knew by using DQ and ZQ we can find out the relative signs of the coupling. That is fine. Up to that we have gone. Now I will take one more simple application of the multiple quantum before we jump onto altogether a different topic today, that is called solid state NMR. So, this another application of multiple quantum is spin system filtering. Okay, we will start like this. The multiple quantum, how we can use for spin system filtering, can be understood by a simple example on a big molecule like this. And now the protons of this molecule, there are 3 phenyl groups here for this molecule, and the protons of this phenyl group are coupled among themselves. For example, AMPX here and 4 protons here and 4 protons. Of course, forget about OH. All are coupled among themselves. They form coupled group of spin system. Okay. So now I want to tell you one thing: how we are going to get, how many transitions we are going to get, and how difficult it is to analyze this single quantum spectrum of such molecules for reason of spectral complexity. If you consider the proton A can have a coupling with M, give rise to JAM. It can couple with AP, JAP, and then couple with X, JAX, and similarly MX and MP and also PX, all couplings. There is A spin in this phenyl ring. A spin gave us 3 couplings, M will give to 2, P gives to 1 coupling. So many couplings are there. Okay, and this forms a coupled group of spin systems. Similarly, this forms a coupled group. This also forms a coupled group of spin system. There are 3 independent group of coupled spin systems are there in this molecule. Okay. Now, how do we know they are independent? Because this group will have a coupled group of protons, will not couple to this phenyl ring at all. They are separated by several bonds, and you believe me, there is no coupling of any of these protons with any of these protons. These 2 form 2 independent spin system. Similarly, this and this form 2 independent spin system. There is no coupling between these protons to these protons at all. And similarly, this phenyl ring and this phenyl ring are also uncoupled. There is no coupling at all. Okay. So these form 3 independent 4 coupled spin systems. Please remember, I said what is the maximum quantum we can detect in such systems? If you consider now a big molecule, but 3 groups of coupled spin systems are there, 4 spins. So you can have 4 quantum spectra possible. 3 independent 4 quantum spectra can be detected from this. For example, now I look at this one. Before we go for this, how many transitions we get in single quantum? So based on that, we want to see, can we do this in spin system filtering? That we will understand. I will consider only phenyl portion of one of the rings. Now I label these protons are A, M, P and X. Here A, M, P and X. Now I want to understand how many peaks we expect at this chemical sheet of A spin. All are independent spins, chemically inequivalent. Now if I want to look at the chemical shift of A, that means A is an active spin. It is undergoing flipping like this. A will undergo flipping. Then what will happen? As I said, it will couple with the passive spins. A can couple with M, P and X, 3 different protons. Okay. Now it can give rise to AM coupling, AP coupling and AX coupling. Okay. That means it will become, A will split into doublet, doublet of a doublet and doublet of doublet of doublets. So it will give rise to 8 lines. Just if you look at the chemical sheet of A in this molecule, A spin should give rise to 8 lines, assuming they are weakly coupled, and these 8 transitions are detectable. It will be doublet of doublet like pattern. Then what happens to M? If M is undergoing flipping, M gives rise to again coupling with A, coupling with P, coupling with X. That also should give rise to 8 lines, D. It will become doublet of doublets. Very interesting. So we know for each of these spins will give 8 lines. So A will give 8, M will give 8. Similarly, P and X also gives 8 lines each. So how many peaks we get? Totally 8 into 8 into 4 spins, 32 peaks. But there are 3 such phenyl rings. So that means there are 96 transitions possible that can be detected in this molecule with 3 phenyl rings which are well separated, isolated. Now remember, all are phenyl groups. Generally in the proton NMR spectrum, the peaks on the phenyl groups come somewhere around 7 ppm. So all these peaks will overlap. That's what I showed you in one of the earlier examples. All these peaks will overlap. Now, to identify this is not an easy job. So, what we have to do, total we have 96 transitions. The analysis is going to be complex. It is going to be really tough task, challenging. How do you overcome this? The simplest solution is detect the highest quantum NMR of such molecules. Now, as I said, there are 3 groups of phenyl rings, each of them containing 4 coupled spins. The highest quantum detectable is 4th quantum. So, if you do non-selective detection of 4th quantum, you are going to get 3 peaks in the 4th quantum dimension. You can separate out each phenyl ring, the peaks pertaining to each phenyl ring in the 4th quantum dimension. So, that is what you can do. So, the 4th quantum single quantum correlation experiment, if you do using the pulse sequence which I showed earlier in the previous class, which is a homonuclear multiple quantum coherence peak, then you are going to get 3 cross sections here in the 4th quantum dimension. This is the 4q dimension, this is SQ dimension. This is called 4q SQ correlation spectrum. So, now take the cross section of this, it identifies 4 protons of one phenyl ring. This identifies 4 protons of one phenyl ring. This will identify 4 protons of one phenyl ring. That means, if you take a projection of this, it is like a one dimensional spectrum in the SQ dimension. That means, it will be a complex spectrum. What did we do by doing this? By doing non-selective excitation at 4th quantum, what did we do? We separated out the peaks corresponding to each phenyl ring. That is what we did. So, it will significantly simplify my analysis. My analysis becomes fairly simple. Okay, that is what happens. Now, 3 peaks in the 4q dimension indicates that peaks from 3 phenyl rings are separated out. That is what it is. And where do these come? That we already discussed. These 4, all the peaks corresponding to this phenyl ring comes at the chemical sheet of the 4 protons of that phenyl ring. Similarly, for example, this comes at the chemical sheet of the 4 protons pertaining to that phenyl ring. This is what happens. So, based on the sum of the chemical sheets of individual protons in each of these phenyl rings, we were able to separate out the 4th quantum spectrum using 4th quantum all the phenyl rings. This is called spin system filtering. This enables easy analysis of the complex spectrum when there is a severe overlap. Okay. Now, we can also use this to detect heteronuclear couplings. That is also possible. And I will take this example. For example, in a molecule like this, each phenyl ring gives rise to 32 transitions, each 4 protons. Each spin gives rise to 32 transitions, spin system. Here is one spin system for 4 protons. I am talking about only 4 protons. Right now I am not talking about fluorine. And then this fluorine. This phenyl ring gives rise to 32, this gives rise to 32. But if it couples with fluorine, 32 will become 64. But fluorine coupling will seen in the proton spectrum. Okay. And the peaks which are coupled with fluorine, this fluorine is splitting, you will see only in the fluorine NMR spectrum. That is what we have been discussing. So, we should get in principle 32 into 2, 64 into 64 here plus 64, you should get 128 lines for this molecule, simple molecule. Okay. So, total 128 transitions you can think of. Easily you will get it if you take a one dimensional NMR spectrum of it, this is what you are going to get. Okay. Fine. So, how to identify the transitions pertaining to each of these 2 spin systems? Just now we discussed simple homonuclear 4th quantum experiment you do. That is what you do. Simultaneously flip all these 4 protons from alpha to beta 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 and vice versa. All of them from plus to minus 2 to plus 2 and vice versa. Then, so all the 4 protons are treated as a single superspin called an active spin, 19F is a spectator spin. So, fourth quantum gives you a single peak because all 4 protons are simultaneously flipping. But remember, fluorine is also a spin half and it is a passive spin. It has spin states alpha and beta. So, it will couple to these 4 protons. That means the fourth quantum, the single line will be a doublet because of coupling with fluorine. That is exactly what is going to happen. Okay. So, now again these two are independent 5 spin system. In NMR jargon, we call them as AMPX spin system, AF, MPX, whatever that spin system you can call, 5 spin system. This is also 5 spin system. So, 4 homonuclear, 1 heteronuclear spin is there in each ring. What we will do is, again, since there is no coupling between interphenyl rings, we consider them 2 independent spin systems. So, weakly coupled spin system and first order analysis is easy to do, we can do that. So, we do the fourth quantum NMR to separate out the peaks pertaining to each spins. Very interestingly, peaks separated out here. This correspond to one ring, one region corresponding to the peak corresponding to one phenyl ring, for example 7, 8, 9, 10. This correspond to phenyl protons 1, 2, 3 and 4. All of them have been separated out. But here interestingly, you may notice one more thing here. What is that you are noticing here? Each line is a doublet. This is a doublet, this is a doublet. What is a doublet separation corresponds to? This doublet separation correspond to coupling between fluorine with each of these protons. So, it is a sum of 6, 7, 6, 8, 6, 9 and 6, 10 coupling that gives the separation. Similarly, this separation correspond to sum of 1, 5, 2, 5, 3, 5, 4, 5 J couplings. That is why in the fourth quantum each peak is a doublet. Now, where does this peak come? At the center of each of this doublet, it corresponds to sum of the chemical sheet of all these 4 protons here and these 4 protons here. So, that you are going to get 4 protons here and 4 protons here and their chemical shifts are here, very easy. Okay. What more you are going to get in this spectrum apart from spin system separation? Very interesting thing is, you can see this correspond to this ring, this correspond to this ring. If you take a cross section along this, you will take a one dimensional spectrum, okay, where chemical shifts individual protons. In addition to that, proton-proton couplings can be studied here, can be understood. You can get proton-proton chemical shifts if you take the cross section of any of these things. Another interesting thing, if you notice, here this is tilted in this direction, cross sections. Here this cross section, one of them is tilted in this direction. What is that? What that is going to tell you? It tells you that the sign of the coupling between this and this are completely opposite. They are opposite in sign. Relative signs of this coupling and one of these proton couplings are opposite. If this is positive, this is negative or vice versa. So, it gives you the information of the sign of the coupling. Of course, this displacement of the cross sections also gives me heteronuclear couplings. You can get lot of information from this 4q SQ spectrum. Simplify the spectrum and you can get HH coupling by taking the cross section. Direction of the displacement of the cross sections gives you sign of the couplings. Also at the same time you can measure the heteronuclear coupling. Simple non-selective excitation of one of the fourth quantum spectrum in this molecule, if one of the spin fluorine is a passive spin, give a lot of information for us. You understood how we can utilize the multiple quantum technique for spectral simplification and getting the relative signs of the coupling and of the heteronuclear couplings and also simplify the spectral analysis. Now, this is with that I will give you one last example. What happens when one of the two coupled spins has a negative magnetic moment? That we did not discuss. Remember, I said when I was talking in the very first class, if you put a gamma nucleus with a positive gamma, its sense of position is one direction. If you put a nucleus with a negative gamma in the magnetic field, its sense of position is in the opposite direction. This is what we understood. Okay. Now, if you want to use this thing to find out what happens if I have one of the spins has a negative magnetic moment. Consider for example nitrogen 15 and proton. Nitrogen 15 has a negative magnetic moment. Proton has a positive magnetic moment. These two have opposite gyromagnetic ratios. As a consequence, they start spinning in the opposite directions. Now, this understanding tells me that double quantum in such situations behave like zero quantum, because they are already opposite gyromagnetic ratios. They will be spinning in the opposite direction. So, double quantum instead of adding will subtract. Okay, if you want to measure the chemical shift in the double quantum, we said there is sum of chemical shift is the frequency at which it comes. Instead, it is at the difference of the chemical shifts. It tells me. So, dq behaves like zq when one of the spins is having a negative magnetic moment. Similarly, if you go to zq, zq behaves as dq. Same way, instead of subtraction, it gets added up in the double quantum dimension. See, this is what happens. The sense of precisions are opposite. If this is proton is persisting like this, nitrogen is persisting in the opposite direction. So, it's exactly do an experiment with a molecule like this. It is a double quantum experiment taking nitrogen 15 into account in its natural abundance. Now, nitrogen 15 proton double quantum you can do. Now, this is coupled to this, this is coupled to this. Now, it is a 4 coupled spin system. Now, there are 2 possible double quanta here. This nitrogen and this proton. Let me remove that. Okay, this nitrogen and this proton can give us a double quantum, and this nitrogen and this proton can give us a double quantum. Each time fluorine and another leftover proton are the passive spins. With that knowledge, if you do a double quantum non-selective excitation here, you get 2 double quantum spectra which is plotted here, and one of the separation gives us you coupling of H2 proton and fluorine, and then other one gives you another coupling. Okay, this is and you can see this separation here. You can measure, and that will give rise to coupling, some of the 2 couplings which we have been discussing. So, this is what we can do. The same thing if you do zero quantum, as you can see here, the separation is larger than this one. See, this is dq. So, that means in this case zq instead of subtracting is adding up. That is the advantage. You should remember, when you have one of the spins is having a negative magnetic moment, Z0 quantum spectrum, the separation coming because of the coupling between the active spins and passive spins is not getting subtracted, but getting added up. So, this is what it is, and with this you can get the sign of the coupling. I mean, if you are looking at the tilt of the displacement, you can get all the information. So, like this you can have this type of molecules simultaneously. You can have, if I take NH double quantum, you can have 2 fluorines simultaneously as the passive spins. You can get coupling from the 4th quantum dimensions. So, this is exactly an example for this. I mean, in the double quantum dimension. In the double quantum dimension, if you do double quantum of nitrogen proton, these 2 are passive spins, and you can measure the separations and get HF couplings, NF couplings, everything, including the relative signs of the coupling based on the displacement vector. So, this is what I was about to discuss about the multiple quantum. This is an example, same thing for the ZQSQ correlation of this molecule. So, what I am going to tell you, what I want to tell you as of today, before completion of the multiple quantum is, in the multiple quantum we discussed a lot about how we can get multiple quantum and what are the conditions required to observe the multiple quantum, and how the passive spin split the highest quantum spectrum, in case of if there is a passive spin, how do we get the relative sign of the coupling in the homonuclear spin case and the heteronuclear spin case. All those things we discussed. This was very, very interesting application of multiple quantum. Mind you, it is not directly detectable, they are forbidden transitions. All transitions other than change in the magnetic quantum number between 2 energy states, which is either +1 or -1, are considered as multiple quantum, including zero quantum. They are called multiple quantum transitions. We have to detect indirectly in a 2-dimensional way. It is called DQSQ correlation or ZQSQ correlation. 4 QSK like that. It is a correlated spectrum. So using the correlated multiple quantum spectrum, we have several applications: relative strength of the coupling, spectral simplification, and spin system filtering. Everything we understood by taking a lot of examples. And also we understood what happens if one of the spins has a negative magnetic moment. We took the example of one of the molecules where nitrogen 15 is present. If you want to say nitrogen 15 proton double quantum, then other proton and fluorine were passive spins, and that gives us the splitting. But one important thing is they rotate or persist in the opposite directions. It means double quantum behaves like a zero quantum behaves like a double quantum. It means addition of couplings in the dq dimension is a subtraction in dq, and subtraction of the couplings in the zq dimension is the addition of the couplings. Similarly, chemical shifts come at the difference here and it comes at the sum here. So like this we had discussed and understood lot. We can utilize this multiple quantum NMR at appropriate places to find the utility of these things. It is widely used, and of course it could be homonuclear and heteronuclear multiple quantum. I have been discussing all along only about homonuclear multiple quantum. Even though heteronuclear spin is present in the molecule, you can also have heteronuclear multiple quantum. One of the example we saw is nitrogen 15 proton. It is heteronuclear multiple quantum, and we discussed homonuclear multiple quantum also. So everything is possible. The pulse sequence for the heteronuclear multiple quantum is slightly different. I did not show that. And zero quantum detection is also done in a slightly different way. For example, how do we select a particular quantum? We can use gradients, okay, in the homonuclear case, especially even in heteronuclear case also you can do. If you want to select a particular quantum, you have to calculate what is the gradient ratios between, if you want to select first quantum or fourth quantum, accordingly you have to apply the gradients so that you are going to get select particular quantum of the spectrum in a n coupled spin system. But how do you select the zero quantum? That is a trick. I did not discuss that because of lack of time, but you please understand this cannot be done by applying gradients. This can be done by applying what is called phase cycling. Remember, we discussed about the phase cycling, we discussed about the gradients, application of the gradients for selection of coherent transfer pathway. Exactly here we can adapt the phase cycling and select the zero quantum detection. We can zero quantum only we can detect and analyze that. Although I showed spectra of double quantum, zero quantum, etc., I showed the pulse sequence also for it is same, but the selection of particular quantum like double quantum or any multiple quantum can be done by gradients, whereas in the case of zero quantum you have to do it only by phase cycling. So I think I have given enough of information about multiple quantum. You can start applying it. What are the advantages, how you can analyze the spectrum, everything we have discussed a lot in the last 2 or 3 classes. So what I am going to do, I will stop here. Now the time is also getting up. So what we will do is next class we will start discussing about completely different topic called solid state NMR, where I will be introducing new type of experiments. How do you get the spectrum, high resolution spectrum in the solid state by adapting certain experimental techniques. So we will come back and continue with the solid state NMR in the next class. And I remind you, all these things information is important. The spins do not know whether it is a solution state or solid state. Only the interaction parameter, the types of interactions are different. Okay. So we understanding what is the type of interaction that are present in solids, which are different from like liquids, we can design new experiments to get high resolution. So we will come back and discuss that in the next class. I will stop here. Thank you very much.